The aspect of neuroinflammation that I'm going to discuss is this molecule MCP1, which we learnt about earlier. This MCP1 is also called CCL2. It's been shown to have roles in various neuroinflammatory disorders, including Alzheimer's disease, multiple sclerosis, stroke, and as we learnt this morning, or earlier, sorry, the MCP1 also plays a role in the neurological changes found in a model of chronic liver disease. In all of these diseases, a role for MCP1 as a chemoattractant to recruit and activate microglia and infiltrating monocytes has been assigned. But we wanted to assess what role this plays in hepatic encephalopathy due to acute liver failure. The mouse model that we used is the azoxymethane model, and in this model, at various time points after injection, we assessed the presence of 5 different reflexes as well as the presence of ataxia. These were given a score out of 2 being that it was completely present and everything was fine, 0 being, everything's gone pear-shaped for them. And at each time point, we summated these scores to give an overall neurological score. And you can see that it gives a nice indication of the neurological decline as we're going. Then at various stages after azoxymethane injection, we harvest the liver and brain for molecular analysis, and they are indicated here. So the first experiment that we did was just to confirm that in our hands we also got a neuroinflammatory response. And this is IBA staining, and you can see here that you do actually get an increase in the number of microglia after azoxymethane. And there's a change in morphology, which I'll show in more detail a little bit later. So using this model, we have an increase in MCP1 expression by real-time PCR at a very early early stage after injection of azoxymethane. This is by real-time PCR. Then if we just take the minor time point, we assessed MCP1 protein expression by EIA, and you can see that it's also upregulated there. Now, in the brain, there's a number of different cell types that can produce MCP1, but in our hands, the MCP1 immunoreactivity co-localizes quite strongly with the neuronal marker nu-N, suggesting a neuronal origin for MCP1. So we then wanted to see what role MCP1 might be playing. We blocked the 2 receptors, CCR2 and CCR4, using specific antagonists. And you can see our azoxymethane is in pink here. The 2 different blues are the different antagonists, and this shifts the neurological curve to the right, which suggests that it is neuroprotective and delaying the neurological decline. And you can also see that indicated here by the time to coma. I will point out, and I don't have the data here, but this had very little effect on the liver damage. And so this was a neuroprotective effect rather than a hepatoprotective effect. And in addition, you can see that we have the ramified microglia here in our vehicle, more amoeboid levels of, more amoeboid shape of our microglia. But after injection, co-treatment with the CCR2 or CCR4 antagonist, they do go back to a more inactive state. And it also decreases in prevalence, and this is kind of indicated here as well. So in looking around and trying to figure out what else might be playing a role in the CCL2 MCP1 effects in acute liver failure, we came across this molecule called fractalkine. Now this is also known as CX3CL1. It's a very unique chemokine. It's the only member of its family. It's expressed in relatively high levels in the brain under physiological conditions. And its receptor is expressed exclusively in microglia in the brain. Now, it's thought that the fractalkine receptor axis acts as an anti-inflammatory effector to suppress aberrant microglial activation. And as you would expect, the expression of fractalkine is reduced in a number of neuropathological conditions where neuroinflammation is a key feature. And in a number of these conditions, there is a reciprocal relationship between fractalkine and MCP1. So in our model, indeed, we do see a decrease in fractalkine expression at the earlier time points. As well, we also see a decrease in the fractalkine receptor expression. I mentioned that fractalkine receptor is exclusively in microglia, but fractalkine in the literature has been shown to be expressed by a number of different cell types. But in our hands, once again, fractalkine co-localized predominantly with mu N, suggesting a neuronal origin again, similar to MCP1. So we wanted to figure out what happens if we restore or increase the amount of fractalkine in the brain. And so we did an ICV injection of the soluble component of fractalkine. And again, you can see the ICV injection of fractalkine shifts our neurological score curve to the right, suggesting a neuroprotective effect, and increases the time to coma. And obviously, as you would suspect, because this is a direct injection in the brain, this had no effect on the liver and the resulting liver damage. So similarly, you can see that there is an increase of microglia incidence here, or number, that is reduced with the treatment of soluble fractalkine. So one question that we keep going back to is, what is being released from the liver that can be causing all these changes in the brain? And one thing that we focus on in my lab is bile acids. I will point out we have a talk tomorrow that goes into a whole bunch of bile acid signaling, and so I'm not going to steal my postdoc's thunder. I'm going to be really brief on the background and rationale here, but we do know that bile acids levels are increased in the serum after liver damage due to an inefficient bile acid recirculation. So the first thing we wanted to do was to assess whether bile acids are actually increased and are getting into the brain in our model of acute liver failure. And so we perfused the animals to remove the blood and then assessed the total bile acid levels in the cortex, the frontal cortex, using a total bile acid colorimetric assay. Wrong way. And you can see that there is an upregulation or an increased incidence of bile acids, total bile acids in the brain. Some may question, actually I question, the specificity of this colorimetric assay. So we did a second strategy where we injected mice with chololysylfluorescein. This is a fluorescent bile acid derivative that has been shown to be transported with exactly the same kinetics as an endogenous bile acid. But we injected this IV 1 hour prior to the injection of azoxymethane, and then assessed the amount of fluorescence in the brain. And indeed, we still see an upregulation or increase in the fluorescence in the brain. So we are confident that there is an increase of bile acids gaining entry into the brain. So what? The next thing we wanted to do was to see if we can remove those bile acids. We used the bile acid sequestrant cholestyramine. Mice were fed a diet enriched in this cholestyramine. And we had to kind of get a treatment regime such that the serum levels were decreased, but there was minimized compensatory upregulation of bile acid synthesis in the liver, which we didn't want. So we figured out that about 2 days we can get this nice decrease in serum bile acids without having a significant problem with the endogenous new bile acid synthesis. And when we injected these mice with azoxymethane, again we see this shift of this neurological curve to the right and indicating a delay in the neurological decline and an upregulation, an increase in the time it took for these mice to go into coma. So what? Does that have anything to do with inflammation? We believe it does. The first thing we did was to take primary neurons, treat them with cholic acid or taurocholic acid for 4 hours, and you can see in these primary neurons we can get an upregulation of MCP1 and a concomitant downregulation of fractalkine. And then in our in vivo model, treatment with cholestyramine seems to eliminate the upregulation of MCP1 seen after azoxymethane, as well as eliminating the downregulation of fractalkine seen after azoxymethane here. So to summarize the data that we have, MCP1 is upregulated and fractalkine is downregulated in the frontal cortex after azoxymethane. We believe strategies to block MCP1 receptors or increase soluble fractalkine are neuroprotective against AOM-induced neurological decline. And lastly, the changes in MCP1 and fractalkine may be attributable to their effects of the effects of bile acid signaling in the brain after AOM injection. And we have a working hypothesis for the model, for the mechanism of this, and this has a lot more data on it than I was able to show you today, but we believe that bile acids are affecting fractalkine and MCP1 expression by two different mechanisms, excuse me, but the bottom line is that we believe bile acids are dysregulating the balance between pro-inflammatory and anti-inflammatory cytokines in the brain, and therefore contributing to the inflammation seen in acute liver failure. And then it just leaves me to acknowledge my lab members and my funding. We're happy to take any questions.